Here's a solution to the worksheet that you did for homework assignment 4. Just want to make sure that all these pieces were clear. Most people were okay with this, but there are a few that were not. When we have a symmetric distribution, and I know that one of these are kind of craggy looking because we only have 100 people, so histograms typically turn out to be kind of bumpy when you do that. But we're going to say these, if we had more and more data, would look more and more symmetric and bell-shaped. The main thing is that when we know the mean and standard deviation for one of these distributions, that we can go ahead and label this bell curve with our center point and our 3 standard deviations in either direction. And we'll be doing that a lot, so we'll just get used to it. In this one, it says the mean for females, which is the one on the left, 64.1 inches. So 64.1 will be about there. And it says our standard deviation is 3.0. And so that means that every time I want to go up a standard deviation, I should add 3.0. So one standard deviation above will be 67.1. 2 standard deviations above will be 70.1. And 3 standard deviations above will be 73.1, which is out here. So that's what 3 standard deviations up look like, and then 3 standard deviations below. I will subtract my standard deviation 3.0 for each one of those. So starting at the middle, 64.1, subtract 3.0 will take me to 61.1. Subtract 3.0 again, that'll take me to 58.1. And subtract 3.0 again will take me to 55.1. So adding those tick marks for the standard deviations is going to be important for our understanding, and in particular, it will help us understand what z-score represents. All we're doing when we calculate z-score is asking where the observation fits in terms of the tick marks rather than in terms of inches. So I'm going to go ahead and label my male heights as well. That one's a little harder to do the arithmetic, but you probably need a calculator for that because my standard deviation is 4.3. Which is a little bit more involved for adding and subtracting. But 68 will be somewhere in here. So this will be my mean, around 68. Adding 4.3 to that will give me 72.3, so somewhere in there. Adding 4.3 to that will give me 76.6. And adding 4.3 to that gives me 80.9. So those are my 3 standard deviations above the mean. And then I can do the same thing going below the mean. 68 minus 4.3 is 63.7. So right in there. 4.3 less than that is 59.4. So in there. And then 4.3 below that is 55.1. So I can label the tick marks for each standard deviation, starting with the mean being in the middle. And so once I've done that, then I have a natural interpretation for z-score. So for my female observation here, it tells me I have a 70-inch tall female. And so the standard deviation formula is the observation minus the mean. For females, the mean was 64.1, divided by the standard deviation. Standard deviation for females was 3.0. So keep in mind that I'm getting those values, 64.1 and 3.0, coming from up here. Those are given to me as the statistics about the mean and standard deviation of the female population or the female sample. For males, I'm talking about a 63-inch tall male, and again, the z-score formula is subtract the mean. For males, the mean is 68. The standard deviation is 4.3, and again, those numbers come from the problem. So for women, or for the woman, the 70-inch tall woman, we have a z-score of 1.96, which means in terms of the tick marks that that woman is almost to the second tick mark above the mean. And if we go look to see where a 70-inch woman would be, she would be right here, just before the second tick mark above the mean. So the 1.96 is telling you how many tick marks she is, not how many inches she is above the mean. And so almost 2 tick marks above the mean is right there. Similarly for the man, we can do this calculation. It's about negative 1.16, looks like. And so that is a little more than 1 standard deviation below the mean. The negative sign there means that you're going to be below the mean. And if we look for where 63 inches is on the male distribution, this is 63.7, so 63 is just over there. Again, a little further away from the middle than 1 standard deviation. So it's 1.16 standard deviations below the mean. So in terms of being able to measure how unusual a data value is, just keep in mind that the middle of your distribution is the number that would have a z-score of 0, right? If I put this mean 68 into this formula as my observation, I get 0 for the z-score. So the average of your distribution is always z-score 0. So that means that the further away from 0 you are, the less average you are. So in this case, the woman's score is more unusual than the man's because it's further away from 0. So 0 z-score is average, and the further you are from a 0 z-score, positive or negative, the further away you are from average. All right, the second part of this homework set was to actually just see how the empirical rule shakes out in terms of the real data. So I've given you here the real 100 values of male heights that made up the graph that's on the top right. And we're just going to examine whether the empirical rule holds or how close it is to holding. The values that go in the blanks for both of these sentences come from the picture. If we already drew it and labeled it, up there, the picture on the right was the males. And so we already figured out that 1 standard deviation from the mean is 1 tick mark above and below the middle. And so that would be, 63.7 inches is 1 standard deviation below the mean, and 72.3 inches is 1 standard deviation above the mean. And I'm getting that because I can look right here and see that that's 1 tick mark below and 1 tick mark above. And if you remember how we got those tick marks, you could see how you would get it even if you didn't have the picture in front of you. So for 2 standard deviations, I do the same thing. I look to see what's 2 tick marks below the mean in my picture. So that's the 59.4 and the 76.6. That's the value that's 2 tick marks below the mean and the value that's 2 tick marks above the mean. And so finally, all I'm going to do down here is count how many of these real data values. There's 100 of them, so it'll be easy to convert to percentage. But we can count how many data values really fall in between those 2 numbers. I'll do the second one first because there's going to be more of them that are in there, and so it'll be easier to just count the ones that are not. So I'm going to do that by just circling them in red. I'm going to circle every height in this table that's not between 59.4 and 76.6. So here are the ones that are not. 58.4 is not in between those 2 numbers. Neither is this, and neither is this. So those 3 values are definitely not in between 59.4 inches and 76.6 inches. On the high end, 77 and 83.5 are the only data values that are not in between those things. And so that means so since it's 100 values altogether and 5 of them are not in between, then that means that 95 of them are in between those 2 numbers. So now if I look at the first statement, I can just continue my list of things that are not in between those 2, and I'll just keep doing that actually I'll circle these in green. I'm going to circle the additional numbers that are not in between 63.7 and 3, these two values up here. So in addition to the red ones, these are not in between 63.7 and 72.3. So those are all the ones that are too small. Those are all the ones that don't make it all the way up to 63.7. And then on the high end, here are all the values that are not smaller than 72.3. So that's the extent of them. The ones that are circled in red and green are the ones that are not in between 63.7 and 72.3. So because these are groups of 10, I can count them pretty quickly. There's 10 of them here. There's 10 of them here. That's 20. Here's 5 more, 25. 2 more is 27. So I've circled 27 altogether, and there were 100 total observations. So the 27 are not in between. That means that 73 of them are in between. So remember, the empirical rule predicts that there are about 68% within 1 standard deviation and about 95% within 2 standard deviations. And we can see with this table of data that those numbers are about right. In fact, for this one, it was exactly 95%. 95 out of 100 is 95%. 73 out of 100 is 73%, so it's not quite that, but we at least get the idea that, that these numbers are in the ballpark for a normal set of data.